This video is going to be like our first video for chapter 15. I'm mostly going to go through example questions, and so if you haven't read the textbook on this section, you really should first. Let's start with this question. Well, I hope you did read the book like I asked, and if you did, then you would know the answer is B, or you may have known from previous experience. So let's talk about thermal expansion a little bit. Again, I'm not really going to explain it. I'll let the book give you the fundamentals of it. We'll just cover some cool examples. So here's an example of engineering that didn't properly consider heat expansion. When these railroad ties were laid down, they were laid down really tight. There wasn't any room for change in shape or size. Well, they were probably also laid on a cold winter day when the metal was contracted and was as small as it probably is going to be. So if you lay the metal when it's as small as it's going to be, and you make it really tight, when summer hits and this metal heats up, it's going to want to expand, push out. But if you haven't left it any space to expand, its only option is to bend like this so that overall the length is longer. You get a longer length this way, okay, which is a terrible result if you were the one that needed to use this railroad track. I hope you can see this okay. I didn't have an easy time finding a good picture. The cracks in this building are also a representation of thermal expansion. So when the bricks of this building were laid, it was probably done on a cold day, so the material had contracted and was small. And then when summer hit and you get direct sunlight baking this wall, the whole wall wanted to expand, and so it probably kind of pushed apart and made these cracks. Well, this is probably also increased. The effect is also increased. Now you have gaps that water can get in there. And as we'll discuss later, water, when it freezes, it expands, so it can push that apart even more. So the effect is made worse when you allow water to absorb into it. If you've never seen one of these, this is the road just before a bridge. This was one of the better pictures I could find. You can see there's a river over here. So this road, as we go to the right, is going to be a bridge. At the base of the bridge, where it's still touching land, you'll see these metal teeth things. These are called expansion joints. Okay, and what they're there for is engineers have gotten much better at understanding thermal expansion. So they know that if you're going to build a bridge, that bridge is going to grow in the summer and shrink in the winter. And if you don't account for that, it can really compromise the integrity and the strength of the bridge as a whole. So this joint is there to allow the bridge to change shape or size. This is a good example of thermal contraction. More than likely, this was taken on a cold day. See how wide the gaps are there. I was hoping to find an equivalent picture of the same bridge in the summer, but I couldn't find one. My guess, though, is that these teeth would be much closer together. So in the cold, the bridge has shrunk and now this stretched out, but in the winter, summer, they should come back in together. If you're at home and you have access to your water heater, you should go down and see if there's one of these things. It's a tank. It should be attached to the hot water line. These are called thermal expansion tanks. If you're heating up water, it's going to expand. The water coming into your house is cold. It's always going to be cold. That's what the hot water heater is for. So if you heat that up, then it's going to expand, but that's going to put a lot of extra pressure on your pipes if they're rigid and there's no way for those pipes to expand. So that can lead to a lot of wear and tear over time. This is meant to reduce that wear and tear because when the hot water expands, it can flow into this tank So the extra space it needs to occupy can be used up in here, where it's not going to put any extra pressure on the joints of the pipes. The last example is a classic one. I apologize again for the picture. I just couldn't find any better pictures on short notice. This photo is showing a jar that's being held under hot water. The jar was probably too hard to open, so they're trying that trick of running it under hot water for a while, and then it usually does help to open it up. The cause for this is thermal expansion again, but I want you to consider this. Does the glass expand by the same proportion as the metal lid? Okay, we often think of the metal as expanding, but the glass will expand too. If you're heating it up, it's going to expand. So will they expand by the same proportion? Why don't you think of that? Okay, well, if they did expand by the same proportion, then this would be a pointless method to try because the lid would be just as stuck as it was before. So the reason why this works is that the glass doesn't expand as much as the metal. So the metal is slightly looser than it would otherwise be, and that's why you can take it off with this trick. Okay, consider this question. It's related to the jar. I wish we were in class because I could just demonstrate this to you, but it just isn't the same when you watch it over a video. So we'll try for maybe a conceptual understanding here. The answer is larger. The hole becomes larger. This is a question that students often miss. The common answer is A, it becomes smaller, because in our head what we're thinking, if this is the original ring and you heat it up, doesn't everything expand outward, meaning the center actually expands in like this, so you end up with the smaller circle. This is what the question is asking. Well, one way to prove to yourself that this isn't how it works is just try the whole jar under hot water thing. If the lid actually became smaller on the interior side, then it would be tighter on the glass, and so it certainly wouldn't be easier to remove. Okay, what actually happens is, if this is your original ring, when you heat it up, everything does expand outward, but the ring as a whole is getting bigger. So the hole in the middle is actually bigger than it was before. So this blue here is the original, and underneath I'm showing the larger version. So this is what it would actually look like. Okay, again, just try it for yourself one time. It does work, and so it can't be this left situation. We're going to stick with this idea of thermal expansion, but I want to shift it just a little bit with this question. So try this one. The answer is definitely gases. That's not even close. Gases expand a lot more than liquids or solids due to thermal expansion. Here's an example with some liquid. All right, so you've probably seen one of these thermometers. The original versions of these used mercury inside of a glass tube. It turns out that mercury is toxic, and so if you break one of these or when you dispose of it, you're actually spreading toxic material. So they've switched nowadays. Usually it's some sort of mineral spirit inside. But either way, it has the same function. The thermal expansion of the liquid should be different than the thermal expansion of the glass. If they weren't different, then changes in temperature wouldn't show, it wouldn't register on this. Okay, so let's just assume this was mercury for this question. And they ask, if glass expanded more than mercury, then the column of mercury in a mercury thermometer would fall when the temperature increases, which wouldn't make sense because that would show that the temperature went down when it actually went up. So if you think about it, the glass is expanding more, now there's more volume for that liquid, which would actually lower it in the tube. So it's a good thing for these to work that the liquid inside has expands more relative to the glass. Okay, this is a good question to end on, so really think this one through. Let's see how you did. This is a commonly missed question, just so you're aware. The answer is a bit short. If you miss this one, I guarantee you're not alone. You're probably thinking to yourself, well, on a very hot day, the tape measure should expand. It should be longer than normal. So won't that give you a longer measurement? Maybe the best way to answer this is to show you an example. So let's say you want to measure the distance between these 2 points. And you're going to use a ruler to do that. Okay, well here, according to the ruler that I've chosen, I'm measuring 9 centimeters. Right, well, let's assume this is also made of steel, and now it gets very hot, so we heat it up to a high temperature. That will cause the tape to expand, and I've exaggerated it significantly. It's not quite so dramatic. But now you can see that with the longer tape, see, the heat didn't affect the distance between these two. The tape is now longer, which means I'm now measuring a shorter distance. So if I read that off, that's about 8.2 centimeters. So that's why it's now shorter of a measurement, because the tape measure itself is longer. So the 9 millimeters is longer than it should have been. Well, if you let that tape measure cool off, it will actually shrink down and you can recover the proper measurement. I hope you found this helpful. It was different than some of my previous videos, but I thought I'd mix it up a little bit and try something new. I do have one more video for chapter 15. In the next video, we're going to talk about the thermal expansion of water specifically.